Hello and welcome to the final topic of Unit 12, electrolysis. In this topic, you're going to discover how we can make use of the electricity generated by the voltaic cells you learned about last time to decompose compounds or to remove a metal from a strip of metal and coat it onto a different piece of metal, a process called electroplating. So let's get started. The most important things to remember that will carry through this whole process is electrons leave the negative end of the battery. Always, 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 always. Remember, you start at the anode, electrons are lost there, and the anode is the negative end of the battery. So electrons always leave the negative end of your source of direct current. Electrons always travel from anode to cathode. You start at the anode, electrons are lost there and go through the wire, through the load on fire, they enter the cathode. Electrons always travel from anode to cathode. Plus and minus are just designations on the battery. And anything hooked up to the negative end of the battery is just an extension of the negative end of the battery. And anything hooked up to the positive end of the battery is just an extension of the positive end of the battery. Now, as long as you keep these three things in mind, you'll be okay. People will get confused because electrolytic cells are almost the complete opposite of voltaic cells in just about every way, but not every way, which is where the confusion comes in. So hopefully we can work our way through that. When we decompose a substance, this is not generally spontaneous. Remember, atoms want to form stable octets, and so they bond with other atoms, so they end up with stable octets. They don't want to give that up. And as a result, decomposition is almost always non-spontaneous. Decomposition can only take place if you constantly put energy into the process. As soon as you take energy out of the process, the whole process stops and it can even reverse itself. You can either add enough heat that can break bonds, but you have to make sure that you do it in an oxygen-free environment, because when old bonds break, if oxygen is there, oxygen will be more than happy to form bonds with whatever just had its bonds broken. So you carry it through in typically an atmosphere of noble gas, maybe an argon environment, where the argon has no reason to bond with the atoms that have just been broken apart, and so decomposition can take place. A little easier is to use electricity. You see, to form an ion, metals lost their one and only valence electron. Well, you can force that metal to eat that electron again, using enough electrical current. And nonmetals formed negative ions by gaining electrons. Well, you can force those nonmetals to cough up those extra electrons just by applying enough electric current. So you can use electricity to force metal ions to gain back the electrons they lost when they formed a chemical bond and undergo reduction to metal atoms, and you can force nonmetal ions to give up their stable octets and be oxidized back to nonmetal atoms. And all you need to do to accomplish this is to make sure that your substance is in the liquid phase so that you have freely moving ions, and make sure you put in at least as much voltage as the reaction has in a negative voltage. So we call this process electrolysis, using electric current to break up a binary compound back into its original elements. Let's take a look at an example of this, sodium chloride. So in the decomposition of sodium chloride, chloride is oxidized and sodium is reduced. So in this reaction, we have to figure out a way to remove chlorine's extra electron from it, removing its stable octet. Sodium has a +1 charge. We have to figure out how to force sodium to eat an electron. You see, sodium has a negative reduction potential. All right. It does not want to gain that electron, it has a negative voltage towards reduction. And chlorine has a negative voltage towards oxidation. Remember, reverse the sign. So neither chlorine nor sodium want to do what you want them to do in this reaction. So you're going to have to force them to do it. So calculating the total voltage tells us that we need to put in more than 4.07 volts worth of direct current electricity to force this reaction to take place. We have to overcome chlorine's desire to hold on to that electron, and we have to overcome sodium's desire to not gain any electrons. So here's how it works. First, you take the sodium chloride and you melt it. Now, this is not easy because sodium chloride has a high melting point, like most ionic compounds. But once you heat it up to the point where it melts, now the ions are able to freely move through the liquid. We're going to put electrodes into the liquid sodium chloride. A good choice to use is graphite. Graphite is made of carbon. Now, typically, nonmetals like carbon are very poor conductors of electricity, but because of the way that the carbon atoms are arranged in graphite, graphite kind of flaunts the laws of nonmetallic behavior. Nonmetals are supposed to be dull and non-reflective. Graphite's really shiny. And nonmetals are supposed to be poor conductors of electricity. Graphite is an outstanding conductor of electricity. Not only that, but its melting point is extremely high. We're talking about thousands of degrees. So even though this ionic liquid is really, really hot, over 1,000 degrees, it's never going to be hot enough to melt the graphite electrodes. Also, graphite is completely non-reactive. So it doesn't matter what elements we break this compound into, the elements we form will never react with the graphite electrodes. So graphite is not the strongest material in the world, but it gets the job done. We're going to hook these electrodes up to a voltaic cell. You might recognize this as like a C cell. Now, what do we say about electrons and batteries? Electrons always leave the negative end of the battery. We also said that electrons always go from anode to cathode, from anode to cathode. And we also said that anything hooked up to the negative end of the battery is just an extension of the negative end of the battery. And anything hooked up to the positive end of the battery is just an extension of the positive end of the battery. So electrons will come out of the negative end of the battery and into the graphite electrode. Now, the graphite doesn't want these electrons. However, they're coming out with enough force that the positive ions are attracted to the negative electrons. They can't help themselves. Opposites attract. And when the sodium ions touch those electrons, the sodium ions will gain the electrons that came out of the battery and turn into pure sodium. And the sodium will build up on that electrode over time. So what you can do is just pull that electrode out, scrape off the sodium, and off you go. Next up, the Cl- will oxidize at the positive anode. So here are the negative ions attracted to the positive electrode. How do we know this is positive? Because it's hooked up to the positive end of the battery. So the chlorine ions attract to that positive electrode where it has its electrons stripped from it. Look at the half reaction. The chlorines will give up their electrons to form Cl2-. Now, who's removing those electrons? The battery is. Once the chlorine touches that electrode, that battery will just, it's like sucking the meat off bones of a well-done chicken leg. The electrons just go right in, back to the battery, and the Cl chloride ions turn into chlorine gas. Now, we can actually trap this gas, and then we can use it to do stuff like, I don't know, disinfect swimming pools. So notice that reduction takes place at the cathode, and the anode is where oxidation takes place. The easy way to remember this is an-ox and red-cat. The only difference here is, in the battery, the anode is negative. Well, in this cell, the cathode is negative because negative is determined by the battery. Electrons always go from anode to cathode. Therefore, where the sodium forms is the cathode because the sodium was reduced there, and reduction takes place at the cathode. Here's another example, the electrolysis of water. We take water and decompose it. Now, obviously, water doesn't decompose into hydrogen and oxygen by itself. It either takes a tremendous amount of heat to accomplish, or just the application of a little electricity. You don't even need all that much. Because if we look at these half reactions and we look at their voltages, this reaction is only going to take basically the amount of voltages that a AA battery provides. You're going to want more current than a AA battery can provide, but the voltage will be plenty. So in this reaction, we need to remove electrons from the oxygen, and we need to give electrons to the hydrogen. So let's do that. Water is a terrible conductor of electricity on its own. So what we do is we add sulfuric acid to it to allow the water to conduct electricity better. The sulfate will not be affected by the electricity, and the hydrogen ion, well, we already have hydrogen in this reaction, so it's not going to impact anything. Once again, we're going to put graphite electrodes in because graphite electrodes are not going to react with what forms, and graphite electrodes will not be eaten away by the sulfuric acid that you put into the water. And then we're going to put this again up to a source of direct current. This is the voltaic cell. So if you imagine, here's one beaker, here's the other beaker, there's the salt bridge between them. Oh, that makes your electrolytic cell the load because it's making use of the electric current. Electrons come out of the negative end of the battery, and they go from anode to cathode. Hydrogen in solution, being positive, will attract to the negative ions, and the two H pluses will gain the two E minuses and become H2O. Let's see that again. Let's take another couple of electrons and another couple of hydrogens. 2H plus 2E minus forms H2O. So what happens at the other electrode? Well, the positive electrode, we're going to attract the negative oxide. And so we will take those minus 2s. We'll bring them over to the positive electrode, and the battery will strip those electrons right off of the oxide ions. So there they go. Whee! Why 4 electrons? Each oxygen changes 2 in charge, so 2 electrons will be stripped for each oxygen, but we have 2 oxygens here, so that's why it's 4. Now you'll notice there's twice as much hydrogen as oxygen. In fact, that's what it says here. We're going to form 2 moles of hydrogen for every mole of oxygen. And then you can actually trap this gas in test tubes that have water in them. And as the gas forms and moves up the tube, it displaces the water. It pushes the water out the bottom of the tube. And so what happens is the gas will actually build up inside the test tube. And then you can measure the volume of gas in the test tube. Now think all the way back to the gases and pressure topic. Avogadro's hypothesis says that equal volumes of gas at the same temperature and pressure will contain equal number of molecules. Well, the volume of hydrogen trapped is twice that of oxygen. That means that the hydrogen has twice as many molecules trapped in it than the oxygen side. And this is actually how the formula of water was discovered to be H2O. Not only that, but the mass of hydrogen was taken and the mass of oxygen was taken, and it was found to exist in a 1:8 ratio. And Dalton used this to start his work on discovering atomic mass. So this simple electrolysis of water has vast consequences. And this exact same process was used to decompose many ionic compounds, and a whole bunch of brand new elements were discovered as a result of this. This apparatus right here is responsible for the discovery of more elements on the periodic table than any other piece of technology. It's outstanding. It's typically used to separate compounds that contain group 1 elements or group 2 elements or group 17 elements, 1, 2, and 17. You know, those elements that are so reactive that they're not going to exist in their pure state in nature. Now for electroplating. For electroplating, what the goal is here is to plate one metal with another metal. Why would we want to do that? Well, maybe the metal we start with is strong, but it's very bad at resisting rusting. So what we do is we coat that metal with another metal that may not be that strong, but has the properties of resisting rusting. So another possibility would be you use a particular metal because it's cheap and strong to make something like, let's say, a sink faucet, but it's not that decorative. So what you do is you electroplate it with another metal that's shinier or prettier to make it look better. So electroplating is one way of evenly coating a base metal with a thin coat of another metal. So we're going to attach the metal that we want to plate with to the negative end, the plate 2 to the negative end of the power supply. In this case, it's a penny. We're going to plate a penny with another metal. We're going to attach the metal you're plating with to the positive end of the power supply. So it looks like we're going to silver plate a penny. We're going to take the silver from this bar and surround the penny with the silver using electricity. It's like magic. And then the last piece of the puzzle, we have to put those metals in a solution of that plating metal. So since we're going to plate with silver, we're going to need a silver solution. And remember, nitrate is always a good choice because it's guaranteed to be soluble no matter what. Now, here's how the process is going to work. Remember, electrons come out of the negative end of the battery and into the positive end of the battery. So the positive end of the battery is going to force silver to cough up its electrons. And when it does, the silver will oxidize. The battery removes electrons from the silver bar, forcing the silver to dissolve into the solution. Now, if you look at what's happening on the penny, the electrons come out of the negative end of the battery, and this makes the penny electrically charged negative. This will attract the positive silver ions to it. And as soon as the silver ions touch those electrons, they will be reduced to pure silver. So the silver bar is oxidized by the positive end of the battery, and the silver ions are reduced by the negative end of the battery. If you were to swap it, well, it wouldn't do you any good because you'd need, let's say you had a copper penny and a silver bar, and you switched the battery, and you had a copper nitrate solution, you could coat the silver bar with the copper from the penny. Whatever metal you're going to be coating is hooked up to the negative end, and whatever metal you're going to coat with is hooked up to the positive end. You can make this thicker by just simply letting this process run longer. Now that is all there is to electrolysis at this particular level. So remember, voltaic cells are spontaneous and they produce electricity. Electrolytic cells are non-spontaneous and they use electricity. That's the key difference between them. Well, that is it for this electrochemistry unit. All that remains is organic chemistry. And while I go and actually record those videos right now, you go forth and practice your electrochemical cells, whether they be voltaic or electrolytic. And I'll see you back here for the next unit next time. Take care of yourselves, guys.
Bye.